Swayam Prabha. Digital India. Educated India.
So welcome to the second day of the school. So yesterday we saw, in fact Meghna described the stable matching algorithm and she defined the stable matching problem. Today we will see a generalization of it, which is typically used in school admissions or college admissions. So here, when it comes to college admissions, many students can get admitted to one college. Right? So that is little different from the men-women setting that we saw yesterday. And what is the difference, and that is something I will show today. So there are some different results and some things just carry over from the one-to-one case. So we will not see this in terms of college admissions, but we will call it the hospital residence problem. Okay, so we will assume that the residents are, these are resident doctors. These are the people who typically finish their MBBS coursework and want to get internship in some hospital. And H is the set of hospitals. Now since each hospital can take more than one doctor, so every hospital has a capacity. So if you are thinking in terms of colleges, this is the maximum number of seats which are available in a college, but yeah, here we will call it the capacity of the hospital. So this is how it is described in literature in terms of residents and hospitals, but always keep in mind that this applies to many situations just like college admissions. So first of all, how do we define stability here? So here, of course, a matching is not a one-to-one mapping like we had last time or yesterday, but many residents can get assigned to the same hospital. So we will still call it a matching. So M is a matching. And when do we say that a pair RH is a blocking pair for M? So can you think and come up with a proper definition of stability for this setting? Sorry, say it again. Yes, that is true. So let me also tell that M satisfies this property. So this is a matching or a valid matching if each resident gets one hospital. And we need another condition, that is the condition on hospitals. Yes, so now each hospital gets at most CH many residents. Okay. So we will assume that the matching M satisfies this property, and for this matching M we want to identify blocking pairs. So we want to know how to define blocking pairs with respect to this particular matching M which satisfies both of these. Okay. So let me write this down. R prefers H to M of R. Yes. So this is one, and another one is H prefers R. Now M of H is a set. So we will say at least one resident in M of H. We also need to consider one more case here. So what if H has a vacancy? Right? So in that case, R is also willing to go to H, and H is also in a position to absorb R without even discarding any of the existing residents who are assigned to H. So here it comes, or what we call this as undersubscribed. That is not matched to its capacity. So we say that a matching is stable if there is no such blocking pair with respect to that matching. So is the definition of stability clear? Just a little more extension. Instead of saying that H prefers R over M of H, because M of H is a set, we compare with each resident individually in M of H and R. And if there is at least one resident in M of H who H can throw out and take R, then RH actually blocks. Or if H has a vacancy where R can anyway be taken, in that case also RH will be a blocking pair. So both 1 and 2 should be satisfied. Okay, yes. Okay. Okay, so let me write down one example of this sort. So suppose R prefers H1 more than H2, then H1 prefers R, let's say, over R1 and R2, who are the residents. So let me, for R1 and R2 I will, okay, let's say the rest, we just allow incomplete lists. And suppose H has capacity 2. So I will write capacity like this in bracket. Now if M is the matching where H1 gets R1 and R2. Now is this stable? And suppose R gets H2. So is this matching stable first of all? This is not stable, right? Because R is willing to go to H1 and H1 also likes R more than both R1 and R2. So in fact, liking more than one of them is also fine. But now H1 wants to take R. So who should H1 throw? Say it again. R2, because that is the least preferred one. So H1 will like to have R1 more than R and R2, right? In fact, if H1 throws away R1, then again R1 H1 will be a blocking pair because H1 prefers R1 more than R2. So we don't allow equal, you mean H1 prefers them equally, right? So currently we are not allowing that, and the case becomes significantly more difficult if we allow what is called ties. So we ask them to submit strict preferences. So this is true with college admissions as well, right? You are not allowed to rank 2 colleges at the same place. And even from colleges side, usually students having same marks, the ties are resolved in some way or other, finally going up to the date of births of the students and so on. So yeah, the ties are not kept in the system and there is some way or other which is found out to resolve ties. So we assume that the lists are strict and so H1 has a clear way to decide whether to throw R1 or R2. So, any more question? So now we know now what a stable matching is. So we say that M is stable if it has no blocking pair. That is, there is no pair which is a blocking pair for M. So how do we find this stable matching? So will the same Gale-Shapley algorithm work here? Yes. So essentially this will be the same Gale-Shapley algorithm where residents will propose hospitals. Now hospitals can accept residents either if they have a vacancy or they can throw away one of the residents assigned to them and take the new resident if they prefer that resident. So according to their preferences, they will either throw away an existing resident or if there is a vacancy, they can directly accept the resident. So the Gale-Shapley algorithm is not very different. So I will not write the whole algorithm, but I will just write a sketch because we have seen the complete algorithm yesterday and this is exactly the same or very similar algorithm. So here residents propose in the order of their preferences and hospitals accept if either they have a vacancy so just like yesterday where a person preferred to be matched rather than remaining unmatched, here also hospital doesn't prefer to have a vacancy, it better accepts some resident in its preference list. Or if they have a less preferred resident assigned to them which they can discard. So a very high level sketch but essentially the same algorithm. So again just like the one-to-one case where the order of proposals did not matter, whichever order men proposed, finally a main optimal stable matching came. Even here the same thing happens. So whichever order residents propose, finally the same stable matching is obtained and that stable matching has the property that it is the best stable matching for each individual resident. So each resident gets his best stable partner if this resident proposing algorithm is executed. So output is a stable matching which is independent of the order of proposals. And in fact, this table matching is R optimal or resident optimal. That is, each resident gets his best stable partner in this particular stable matching. So what all properties did we see in the one-to-one case of stable matchings? So now we are dealing with incomplete lists. So in case of the one-to-one setting, what happened when there were incomplete lists? Say it again. Yes, residents could, so in the one-to-one case, some men and women could be unmatched, and we observed that in all stable matchings, the same set of men and women will be unmatched. So let me just recall this result from the one-to-one case. By one-to-one case, I always mean the men-women case where everybody got one partner. So here we saw that every stable matching leaves the same set of people unmatched. What could be the analog of this for the many-to-one case or the hospital residence case? So can you suggest what statement I should write now for hospital residence case? So in case of hospitals, we are no longer using the word unmatched. We are saying undersubscribed instead of unmatched because they can possibly get some residents but may not get up to capacity many residents. So a hospital could be full, which means it gets capacity many residents, or it could be undersubscribed, in which case it gets less than its capacity many residents. So how should I frame a similar sentence for the hospital residence case? Yes, so I will write this potential statement. In every stable matching, the same set of residents is unmatched, which is no different from the one-to-one case, and the same set of hospitals is undersubscribed. Now can it happen that, say for example, if a hospital has capacity 4, can it get 2 residents in one stable matching and 3 in another stable matching? So in both cases it is undersubscribed. Right? So this statement is not violated, but the question is this possible? Can a hospital get different number of residents in a stable matching? Or in different stable matchings? Yeah, so if no, then why do you think it should not be possible? Yes. Yeah, so this is a very good point. So her answer is that a hospital H has capacity CH. So now what if I make CH many copies of this hospital? So I will make the copies H12. So let's say this CH is K. So H1 to HK. Okay, now I say that each of individual hospitals have capacity 1. So we have landed up in a 1-to-1 setting, but we have to be careful about the preferences of residents. So earlier if a resident R has hospital H in his preference list, now what should R have? Yes, so R should now have, H1 to HK in the preference list, not as ties because we don't want the case with ties, but in the same strict order. Yes, what is the okay. So we just fix this order on the copies of H, and every resident ranks these hospitals in this same order. So now we have landed up in the 1-to-1 case. So now here each one has capacity 1, so we don't have the many-to-one setting really. Okay. And if we apply the result of the 1-to-1 setting now, that the same set of people remain unmatched. Now here people means residents and also hospitals. So naturally if C many copies of H remain unmatched, this should be the case in every stable matching here because we have the 1-to-1 setting now. Is the 1-to-1 setting clear what we did? We just made CH many copies of a hospital, every hospital. But it will not happen that some resident, it should not happen that some resident R ranks H1 better than H2, where H1 is one copy and H2 is another copy. If one resident is doing that, and every resident should do that. So this order on the copies of this hospital should be fixed in the preference list of all residents. Okay, so whenever H appears in someone's list, we replace that H with exactly the order H1 to HK. Yes, so if this is H followed by followed by H prime, then I should have H1 to HK followed by H prime 1 to H prime whatever, let's say L, where C of H prime is L. Okay, and so on. So the preference list blow up like this. Okay, so if C copies of H remain unmatched, then that will translate to H getting K minus C residents. So this way of going from the many-to-one case to one-to-one case tells us that every hospital, not only that a hospital remains undersubscribed in all stable matchings if it remains undersubscribed in one stable matching, but it also gets exactly the same number of residents. Okay, so once again going back to the previous page. So this answer is no, and this answer comes by making CH many copies of hospital H. And this we do for each hospital H. So any questions so far? Okay, so the one-to-one case tells us that the same number of copies of each hospital should remain unmatched in the one-to-one case. So the same number should the same number of residents should be matched to each hospital in any stable matching. Now I want to say that even a stronger statement is true, which we don't get from this one-to-one case. By the way, then why are we looking at the Gale-Shapley algorithm in the many-to-one setting if everything works nicely by making copies? So do you see any advantage of looking at the many-to-one case separately if just the copies, making copies work? At least some small advantage we should gain if we want to study the many-to-one case separately. Yes, because if there is no blocking pair here, yeah, so yeah, let me write this down. Although I am not precisely proving these statements. So running Gale-Shapley on, so this I call as a blown up instance, because we blow up every hospital into CH many copies. So running GS on the blown up instance. So this is not difficult to check or convince yourself. So I will not prove this. Gives the same output as running on the original instance. Okay. So what advantage do you see? Since we are getting the same output, we are not doing anything wrong. So the only advantage which can possibly come is through time. So how much time was the Gale-Shapley, how much time does the Gale-Shapley algorithm take on the one-to-one setting? Say it again. Linear? Yes. So the time is, so because every, so in the one-to-one setting, every man proposes every woman at most once. So we can say that this is order m, where m is the number of edges in the underlying graph. So this is for the one-to-one case. Now here, if the many-to-one instance has, so if the many-to-one instance has m edges, how many edges will the blown up instance have? So every edge in the many-to-one instance, how much does it blow up when it comes to many-to-one instance? Sorry, in the one-to-one instance or the blown up instance? Say it again. Correct. So every edge here, that is for this RH, we got these k many edges. Right? So if we assume that the upper bound on the capacities, so what is the maximum capacity a hospital can have? CH, but then it cannot be more than the number of residents, right? Because there is no point in having more capacity than the number of residents available. So we can assume that CH is at most n. So CH is less than or equal to number of residents. So every edge essentially blows up into m into number of resident many edges. So the time also blows up, that is m into again number of residents. I can write mod r for this. Is it clear? So when we blow up, the number of vertices and edges increases significantly, the instance becomes larger, and we get an additional mod r factor in the running time. Whereas if we execute the Gale-Shapley algorithm on this non-blown up instance or the original instance, we are again going to get order of m time. So order of m time if we don't blow up versus order of m times mod r time if we blow up. Right? So we are becoming slower because of this blow up. And rightly so, because it doesn't really make sense for R to propose all copies of H separately, which is what will happen in the when we blow up the instance. So it is really wasteful, and also there are some interesting results which we can't see in the one-to-one setting, but which are evident in the many-to-one setting. So one such result we will see now. So any questions so far? Is everyone convinced that by not blowing up we are at least faster? Okay, so no question? So let me write down the statement again. So we will not blow up really, because we are becoming unnecessarily slow and we are also losing some structure, which we will see now. So we will assume that we are working with the original instance. So in each stable matching, so or let me write down the other way. If H is undersubscribed in a stable matching, so this is the same statement that we saw earlier, then H gets, now I want to say that not only that H gets the same number of residents, which we also deduced from the one-to-one case, but in fact H gets the same set of residents. Okay. So if H is undersubscribed, it cannot happen that it gets one resident in one stable matching but not in the other stable matching. So this is what is called the famous rural hospitals theorem. So the name rural hospitals theorem comes because typically people are unwilling to go to rural areas for internships. So the hospitals which remain undersubscribed are mostly from rural areas, and hence because the theorem concerns the undersubscribed hospitals, it is named as rural hospitals theorem. So first we will see an example. So suppose R1 prefers say H2 over H1 and then H3, or R2 also does the same. So these are residents preference lists. Let me write down hospitals list. So suppose H1 has capacity 2, H1 prefers R1 over R2 over R3 over R4 over R5. H2 prefers R3, R4 and then R1, R2 and then R5. And H3 prefers R1, R2 and R5. And all hospitals, let's say, have capacities 2. So can you point out the two stable matchings here? Yes. Yes. So R1 to H2, R2 to H2. So this is what the resident proposing algorithm will give, because R1 and R2 will propose to H2 and H2 can accept both of them. So they can both get matched to H2. R3 and R4 will propose to H1. They can also both get matched to H1. Now R5 cannot be accepted by H1 because H1 is already full, it has capacity 2. Similarly, H2 cannot accept R5, so R5 will go to H3. So let me mark the same matching here. What is another one? What if hospitals propose? Now remember that hospitals have to propose multiple residents as long as they don't have capacity many residents. Yes. Yes, yes. Yes. So sorry, I said it, I did not say it explicitly, but when R5 proposes H1, H1 already has better residents, that is R3 and R4, so H1 will not accept R5. And even when R5 proposes to H2, the same thing will happen, that H2 has already better residents than R5, so H2 is going to reject. And finally, when R5 goes to H3, H3 has nobody, so H3 accepts. Now if, say it again. Yes, so if hospitals propose, H1 will go and propose R1 and R2 and they will both accept. And then, yeah, H2 will propose to R3 and R4, they will also accept. Now when H3 proposes to R1, R1 again already has a, so let me mark these red partners. So when H3 proposes to R1 or R2, they already have better partners or they are matched to better hospitals, so they are going to reject and H3 will again end up with R5. So here we see that so H1 and H2 are full. The only undersubscribed hospital is H3. It is undersubscribed in both the stable matchings. And as I have not proved the theorem yet, but this is an illustration of the theorem that this undersubscribed hospital always gets the same resident. So you will not find any stable matching where H3 can get something different from R5. Is the same statement true for full hospitals? No, right? Because here we see that in one of the stable matchings, H1 gets R1, R2. In another stable matching, H gets R3, R4. So certainly full hospitals can get different residents in the different stable matchings, but undersubscribed hospitals cannot. So H3 gets the same set of residents. Here the set is of only one resident. And H1, H2 can get different sets. So certainly what the statement that we made in rural hospitals theorem for undersubscribed hospitals, that they get the same set of residents in all stable matchings, is not true for full hospitals, as this example itself illustrates. So for undersubscribed hospitals, let's try to prove this. Yes. So this can only mean that so Nildara's question is that if all hospitals are undersubscribed in a stable matching, then is there a unique stable matching? So this is true, and it also says that every resident will get his first choice, because all hospitals are undersubscribed. They will never come to a stage of rejecting anybody. Right? So this is a very nice observation, and I will note it down. If all the hospitals are undersubscribed, in a stable matching, then the instance has a unique stable matching. And moreover, in this stable matching, a byproduct is that every resident gets his first choice. Since no hospital can reject anyone. Yes, so that is also another point to note, that this also is one of the things which contrasts this many to one case from the one to one case. So in the one to one case, if there is a unique stable matching, that does not mean that every man gets his first choice. The unique stable matching could very well be because I mean, even if there is a unique stable matching, there could be rejections. Okay, so yes, yes, no, no, yes. So this is the other way around is not true. That if there is a unique stable matching, that doesn't mean every hospital should be undersubscribed. So a simple example is when there are two residents and two hospitals, and say the hospitals have capacity 1. 1 capacity is not necessary, but still. So I'll put 1 capacity here, although we can make capacity 2 later on. Yeah. So here the only stable matching that we see is R1 gets H1 and R2 gets H2. Because when R1 and R2 both propose H1, H1 is only going to accept R1 and then R2 has to go to H2. Similarly, even if hospitals propose, when both H1 and H2 propose R1 in whatever order, R1 is going to accept H1 and then H2 has to go to R2. So here we have a unique stable matching, but no undersubscribed hospital. So any other point? Okay, so let's go to prove this rural hospitals theorem. So before I prove this theorem, we want to prove a simple statement. So let's say M naught is the R optimal stable matching and let's say M is any stable matching. Because to prove rural hospital theorem, there have to be more than one stable matching in the first place. Otherwise, it doesn't make sense to say that in all stable matchings, the hospitals get the same set of residents, the undersubscribed hospitals. So the statement will be trivially true if there is only one stable matching. So we consider the case when there are multiple stable matchings. In particular, M naught is the R optimal one and M is any other stable matching. And what I want to say is, so suppose M naught of R is H and H is undersubscribed in M. Okay. So in the resident optimal stable matching, R is matched to H, and in the other stable matching M that we are considering, H is undersubscribed. So can R be matched somewhere else in M? top or at least the best stable choice. Yeah. So just like the case of R5 in the earlier example. So let's say, so the picture is like this. There is R, there is H, there is H prime. R is matched to H in M naught, which is the blue matching, and R is matched to H prime in the yellow matching. So now what can we say about R's preference between H and H prime? Say it again. So why do you say H prime should be more preferred? Uh, yeah, see, the catch is that I did not say whether H is undersubscribed in M naught. Say it again. Yes. Okay, so then, yeah, so if we use the result that we inherited from the one-to-one setting, yes, then H must be undersubscribed in M naught as well, and in fact has the same number of residents. Good. Yeah, so now, see, the point is we have to use the R optimality of M naught. So because M naught is R optimal, it gives the best stable partner to every resident. So in particular, H must be R's best stable partner. But then if H is the best stable partner and H prime is some other stable partner, then R has to prefer H over H prime. So R's preference just looks like H and then somewhere later H prime. But then can M be stable? No, right? Because R is matched to a worse partner in M, and H is undersubscribed in M. So RH pair blocks M. Does it make sense? So R has also gone to worst stable partner and H has also remained undersubscribed, who is R's best stable partner, although may not be the first choice. So then RH pair is going to block M, so M cannot be a stable matching. So what we want to say is, if a hospital H is undersubscribed in M, then it should get every resident that it gets in M naught. So whatever residents H gets in M naught, they should all be matched to H in M. Is it clear so far? So any matching where H is undersubscribed and R also goes to a worse stable partner is not going to be stable. So if H is undersubscribed in M, it should better remain undersubscribed after getting everything that he gets in M naught. So have we ruled out the possibility that H may get some more residents in M? So how do we say? Yes. So let's say H is undersubscribed in M naught and also in M, but then it will be getting different number of residents, right? Yes. 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 So we said that because of the one-to-one case or because of the blown up setting that we saw. So I think I managed to confuse you, although you were saying the right thing. I just wanted to ask why we rule out the case that H is getting uh, more residents in M. And of course that is ruled out now from the one-to-one case where we said that every hospital gets the same number of residents. So you are right in saying that that must be in fact equal. Yeah, yeah. So that is not wrong. Only thing is why we want to conclude that is something I wanted to ask. So same set is something we are proving now, but we know the same number is really true. So here, because M naught H is a subset of MH, only possibility for MH to be different from M naught H is by having more residents. Right? But that is not allowed or that is ruled out because every hospital gets the same number of residents in all stable matchings, which we concluded by just blowing up our instance to the one-to-one setting by making copies of hospitals. So we proved that mod of M naught H equal to size of MH. This we proved from by blowing up. When I say blowing up, I mean we made copies of the hospitals and then we concluded that the same number of residents should be matched to both. Okay. So these two together conclude that M naught H is actually same as MH. Okay. Yes. Yes. But just because we said R optimal, it is a little easier to see. But yes, we can do this with any two stable matchings where R gets two different partners. So we really don't need M naught, but we need some stable matching here where R gets a better partner than H.